Welcome back to the channel. Thank you so much for spending your time here today. If you enjoy calm, science-based explorations like this, please consider liking the video, subscribing, and sharing it with someone who might appreciate it. It really helps the channel grow. I am also curious, what time of day are you listening to this? And where are you watching from? Feel free to let me know in the comments. Thank you again for being here, and now let's begin. In the modern view of physics, there is no clean border where one set of rules ends and another begins. The same framework that describes the behavior of electrons in an atom also describes the stability of matter, the reliability of machines, and the structure of the familiar world. The everyday world appears solid, continuous, and predictable to the senses, while the quantum world is often described as discrete, fluctuating, and statistical. It is tempting to imagine that these belong to separate domains that follow different laws. The contemporary understanding is the opposite. The ordinary world is now seen as an emergent face of the same quantum theory that governs atoms, molecules, and light. Tables, planets, and living bodies are made of quantum systems whose collective behavior appears classical under the right conditions. In this sense, the world of common experience is not separate from the quantum world, but sits on top of it as a useful approximation. The rules that apply in the laboratory when a single electron passes through an experimental device are the same rules that apply when many particles interact in a piece of metal or in a crystal in a mobile phone. The difference is not in the laws, but in how the laws show themselves when enormous numbers of particles are involved and when interactions with the environment constantly disturb delicate quantum states. This way of thinking has practical consequences. Quantum theory is not only a tool to explain the spectra of atoms, the behavior of semiconductors, or the stability of chemical bonds. It has become a working manual for devices that are now engineered deliberately to exploit its more counterintuitive features. Lasers, magnetic resonance, imaging, atomic clocks, and the transistors that underpin modern electronics all rely on quantum ideas, even if they hide those ideas behind stable, predictable performance. In recent decades, a new generation of technology has begun to appear, one that does not merely tolerate quantum effects, but seeks to isolate control and amplify them. These devices include prototype quantum computers, quantum communication links, and sensors that reach levels of precision that classical designs cannot match. In all of them, the strange behavior of superposition and entanglement is not an unwanted complication, but a central resource. Because of this shift, quantum mechanics has moved from being a subject that could once be treated as an abstract concern into something far more concrete. When the theory was first developed, the puzzles around measurement probability and reality could be set aside by some as matters of interpretation. The equations gave results that matched experiments. For many purposes, that seemed enough. Now, however, devices are being built whose functioning depends directly on the structure of those equations and on the very features that caused confusion for the early pioneers. A quantum computer is not just a faster version of a classical machine. It is a different kind of information processor built from physical systems that hold and manipulate information in ways that have no analog in the classical picture. To design, operate, and scale such a device, engineers and physicists must work with the full quantum description not only in isolated atoms, but in larger assemblies of controlled qubits. The same is true for entangled photon networks used in secure communication or for arrays of ultra-cold atoms used as clocks of extreme accuracy. This growing reliance on quantum behavior gives new weight to old questions. Quantum theory is one of the most successful frameworks in science. It has been tested across many scales and in many different kinds of experiment. Yet even today, there is no single agreed view of what the formalism says about the nature of reality. The mathematical machinery is clear. The predictions are clear. What remains open is how to connect that machinery to a mental picture of what is actually happening between preparation and measurement. In the past, these questions might have been left largely to philosophers of science or to a minority of theoretical physicists. Now, as technology reaches deeper into the quantum regime, they begin to have a more practical flavor. When a device relies on the existence of a quantum superposition, it becomes important to understand what is meant by that superposition, how it is maintained, and how it is lost. When components must remain entangled over long distances or long times, the conditions under which entanglement persists become central engineering concerns. Teaching has started to adapt to this new reality. For a long period, quantum mechanics was commonly presented through a historical route. Students would be led through the crises of classical physics, the failure of old theories to explain certain experiments, and the gradual construction of the new theory. Photoelectric effects, atomic spectra, and the planetary picture of the atom would appear in sequence along with the difficulties they posed. This approach helped to convey the sense of confusion and surprise felt by the early researchers, but it also tended to pass that confusion on to new generations. In response, many courses now present quantum mechanics more directly as a finished theory. Students are introduced earlier to its core mathematical structure and to standard examples in which that structure is applied cleanly and then returned to the history with a clearer sense of where it leads. A particularly useful modern entry point is the concept of spin. Spin is a quantum property of particles such as electrons that behaves in some ways like the angular momentum of a spinning object, but it has no simple picture in terms of a tiny ball rotating in space. What matters for the present discussion is that the spin of an electron can be measured along some chosen axis, and the outcome is always one of two values often called spin up or spin down along that axis. In this respect, spin resembles the heads or tails outcomes of a coin toss. The system appears to have only two allowed results, yet, as the more detailed theory shows, an electron does not need to be in a state that corresponds precisely to up or to down. It can be prepared in a state that is a superposition of these possibilities. When a measurement is made, one of the two definite results is obtained, but the statistical pattern of many such measurements reveals that the pre-measurement state contained a structured mixture of outcomes. This basic example, close in spirit to the coin analogy suggested in many classroom explanations, already contains many of the key features of quantum behavior. The idea that a system can exist in such superposed states is foreign to everyday experience. Classical objects seem always to occupy definite positions, carry definite velocities, and possess definite values of any other property that can be measured. When uncertainty appears in the classical world, it is usually attributed to incomplete information. A forecast of rain might be given a certain probability because the atmosphere is complex and the available data are limited not because the weather itself is undecided. Quantum superposition challenges this comfortable picture. In the quantum description, probabilities are not merely reflections of ignorance. They are woven into the way the system is described from the start. The theory assigns amplitudes, mathematical quantities related to probabilities to different possible outcomes. The squared magnitude of an amplitude gives the probability for that outcome when a measurement is performed. Between preparation and measurement, the quantum state evolves smoothly according to precise equations, but the outcomes of individual measurements remain intrinsically uncertain. The central message is that quantum mechanics is not a separate layer of reality confined to locked laboratories and exotic experiments. It is the underlying structure from which the common world arises. The same principles that control the interference of electrons in carefully shielded devices also control the flow of current in a circuit, the emission of light from atoms in a lamp, and the operation of magnetic memories and superconducting circuits. As experimental techniques improve and technologies become more refined, the boundary between abstract quantum theory and practical engineering continues to move. Devices that once could only be imagined as thought experiments now appear as prototypes in laboratories and gradually as commercial instruments. In parallel, the conceptual questions that surrounded the theory from its earliest days are being revisited with new tools and with new urgency. The strange behavior that once seemed remote from daily life is becoming part of the material that future technologies will routinely manipulate. Later sections will explore specific examples of this behavior, but they all rest on this unified picture: one world governed everywhere by the same quantum rules, with the familiar and the unfamiliar joined in a single description. In everyday situations, probability is usually treated as a measure of limited knowledge. When a weather forecast assigns a certain chance of rain, the statement does not suggest that the atmosphere itself is undecided. It reflects the fact that the atmosphere is a complex system with many moving parts, and that no agency can track all of them in perfect detail. A similar attitude appears when a coin is tossed, when cards are shuffled, or when a measurement on an instrument is repeated with slightly different readings. The underlying assumption is that the world follows definite trajectories, and that probability arises only because observers do not have full access to all the relevant information. If more data were available, and if the calculations could be performed without error, the outcome in principle could be predicted with certainty. This view of probability as ignorance is deeply embedded in classical physics. In that framework, particles have precise positions and velocities at every moment, even if no one is watching. Fields have definite strengths and directions at every point in space, even if no instrument is present to register them. A cloud of gas is taken to consist of many molecules in motion, and the pressure and temperature are understood as averages over the detailed microstates. Probabilities enter when those details are too numerous to follow, not because the underlying description is incomplete. Quantum mechanics introduces a different role for probability. In the quantum formalism, the state of a system is represented not by a list of definite values, but by an object that encodes the likelihood of many possible outcomes of future measurements. The theory provides a precise rule that connects this state to probabilities, and that rule is not removed by gathering more information. Even with complete knowledge of how a quantum system has been prepared, the outcome of a single measurement on that system remains in general unpredictable. Only the statistical distribution of many repetitions can be calculated in advance. This feature is not a temporary limitation caused by imperfect instruments or by hidden variables waiting to be discovered. It is built into the structure of the theory itself. When a spin measurement is made on an electron in a particular superposed state, there is a well-defined probability to find the result labeled up and another to find the result labeled down. No further refinement of description within standard quantum mechanics replaces those probabilities with certainties for individual events. The randomness is intrinsic. This intrinsic character is easiest to appreciate when a simple quantum system is isolated and manipulated with care. Spin is again a convenient example because it offers only two distinct outcomes along a given axis, which avoids the complications of continuous ranges of values. If an electron is prepared in a state that corresponds to spin up along the vertical direction, and then the spin is measured along that same direction, quantum mechanics predicts that the result will always be up. In this case, the outcome is certain. However, if the same electron is subjected to a spin measurement along a different axis, such as a horizontal one, the situation changes. The spin state that was definite for the vertical measurement is now a superposition of up and down for the horizontal measurement. The theory assigns probabilities to these two possible outcomes, and when the measurement is performed, one of them occurs. Repeating this procedure with many identically prepared electrons yields a stable pattern of results that matches the predicted probabilities. No method is known within the accepted framework that would allow an experimenter to predict which specific electron will give which outcome in a given run. The pattern emerges only in the statistics. A similar story appears in experiments with photons, neutrons, atoms, and more complex systems. Interference effects and discrete measurement results show that quantum systems do not carry in any straightforward way a set of pre-existing values for all possible measurements. Instead, the theory associates with each possible measurement a set of probabilities that depend on the current quantum state. Changing the measurement setup changes how the state is expressed and thus changes which outcomes are more or less likely. The key point is that there is no single hidden list of definite answers stored inside the system for every possible question that could be asked of it. The apparently simple idea that additional unseen variables might restore classical determinism has been explored in depth. Under reasonable assumptions, tests based on inequalities derived in the 1960s show that any theory that both reproduces the quantum predictions and keeps certain classical notions of locality and realism must fail these bounds. Experiments performed over many decades with increasing control and closing of loopholes have consistently supported the quantum predictions. For someone trained in classical physics, this situation can feel uncomfortable. The idea that probability might be a basic ingredient of the description of nature rather than a sign of incomplete knowledge challenges long-held expectations about how a scientific theory ought to work. Classical theories promise that if the initial conditions and the equations of motion are known, the future is fixed. Quantum mechanics, by contrast, offers only conditional statements of the form that if a system is prepared in a given state and a particular measurement is chosen, certain outcomes will appear with certain probabilities. The evolution of the state between such measurements remains deterministic and smooth, but the link between that evolution and specific observed events passes through an irreducible statistical step. Some interpretations attempt to restore determinism by adding additional structure beyond the standard formalism, while others accept the probabilities as fundamental and reinterpret what is meant by an outcome or by a measurement. Regardless of interpretative preferences, the practical rule that connects quantum states to experimental frequencies is the same and has been confirmed again and again. This distinctly quantum role for probability has important consequences for how information is understood in physics. In classical theories, information can in principle be copied, arbitrarily stored without disturbance, and extracted without altering the system being examined. The probabilities reflect ignorance that could be removed without changing the underlying reality. In quantum mechanics, by contrast, attempts to gain information about certain aspects of a system inevitably disturb other aspects. Superposed states that encode rich patterns of potential outcomes cannot be fully examined without collapsing that structure into a more definite form. There are theorems that make this precise, such as the statement that an unknown quantum state cannot be copied perfectly. This no-cloning feature does not come from practical limitations in the laboratory. It follows directly from the linear structure of the theory. As a result, information in quantum systems behaves in ways that have no analog in classical physics, and probability is woven into that behavior from the start. The shift from probability as ignorance to probability as an intrinsic property of physical systems marks one of the deep conceptual changes brought by quantum mechanics. The equations that govern the evolution of quantum states are clear and compact. They allow precise predictions for the statistics of outcomes across a wide range of situations. Yet the move to a framework in which randomness occupies a central role continues to raise questions about what counts as a complete description of reality. In practice, physicists use the theory as a remarkably accurate tool, designing experiments, predicting results, and comparing data. In parallel, the deeper meaning of the probabilities that appear in the calculations remains an active subject of analysis and debate. What is clear is that the old picture, in which uncertainties could always be traced back to incomplete knowledge of a fully definite underlying world, no longer matches what carefully controlled experiments reveal. At the most basic level, accessible to current instruments, nature presents itself through patterns of outcomes that are constrained by strict rules, yet individually unpredictable. Quantum mechanics captures these patterns by placing probability at the heart of its description, and this choice distinguishes it sharply from the classical theories it replaced. In moving from probability as a feature of descriptions to the concrete behavior of physical systems, it is helpful to focus on a simple object that can be handled in the laboratory and whose properties are well defined. In modern quantum information science, that basic object is called a qubit. The word is meant to capture the idea of a quantum bit, a system that can carry more structure than a classical bit, yet still yields only a limited set of outcomes when measured. A classical bit in the language of computation can be in one of two states often labeled 0 and 1. a coin in an idealized model, serves as an intuitive physical example. Once the coin has landed, it is either heads or tails. A qubit, by contrast, is realized in many different ways, such as the spin of an electron, the polarization of a photon, or two energy levels in an atom or a superconducting circuit. In each case, the system has two outcomes for a certain measurement, but the full range of possible quantum states is richer than a simple either-or choice. To see how this works, it is again convenient to use spin as a concrete case. The spin of an electron along a chosen axis, say the vertical direction, can be measured and always gives one of two results, which are labeled for convenience as up and down along that axis. These labels do not refer to a tiny object literally spinning in space, but they serve to distinguish the discrete outcomes. If an electron is prepared in a state that guarantees the up result when measured along the vertical axis, then that state functions like a definite state of a classical bit. There is no uncertainty in the outcome of that particular measurement. However, the same electron, when examined with a device aligned along a different axis, such as a horizontal direction, does not behave as if it carried a pre-existing answer for both measurements. Instead, a state that is definite for one axis appears in the mathematical description as a superposition of the two possible outcomes for the other axis. The probabilities of obtaining each result depend on how the measurement axis is oriented relative to the state. These probabilities are determined by the structure of the state itself, not by ignorance about some hidden configuration. This idea of superposition is central. A superposition is not simply a statement that the system is really in one state or the other, and that knowledge is incomplete. It is a different kind of description in which the system is assigned complex amplitudes for different basis states. For a single qubit, a convenient choice of basis states might be those that yield up and down along a particular axis. The amplitudes encode not only how likely each outcome is, but also how the different possibilities can interfere in later processes. When a measurement in that basis is finally made, the state appears to jump to one of the definite outcomes, and the probabilities for those outcomes are given by the squared magnitudes of the corresponding amplitudes. In between preparation and measurement, though, the system evolves in a way that maintains the superposed structure. This allows the qubit to carry information in a form that cannot be captured by a simple classical variable that is either in one state or the other at every moment. A coin analogy is often used in teaching to give a rough picture of what is happening. A coin that has landed is either heads or tails. A coin tossed high into the air is in motion and hard to inspect. One might be tempted to say that while it is in flight, the coin is in some mixed condition not yet assigned to either outcome. In classical physics, however, the coin has a definite orientation at every instant. If one had perfect information about its initial conditions and about the forces it experiences, the landing result could be predicted. The appearance of uncertainty comes from practical limitations. In the quantum case, when a particle such as an electron is prepared in a genuine superposition, the theory does not attribute to it a definite value of the relevant property at each moment. The superposition is not merely a reflection of temporary lack of information. It is the full description the theory provides. Only when an appropriate measurement is carried out does a single, definite outcome emerge selected according to the probability distribution encoded in the superposition. Although this behavior does not match everyday intuition, it has been observed and exploited in many experiments. Devices known as spin filters and beam splitters can be used to prepare and analyze superposed states of electrons, neutrons, and photons. By arranging a sequence of such devices, experimenters can show that removing or inserting certain elements changes interference patterns in ways that cannot be explained if the particles always carry definite hidden values for the measured properties. Instead, the outcomes reflect the structure of the quantum state as it passes through the apparatus. The ability to maintain and control superpositions underlies the emerging field of quantum information processing. In such settings, qubits are prepared, manipulated, and measured according to well-defined protocols. Gates that act on one or more qubits change their states in controlled ways, much as logic gates change classical bits. But with the additional feature that gates can transform superpositions into new superpositions. A single qubit in a superposition can be thought of as carrying a blend of possibilities for a chosen measurement, but its full power becomes clearer when multiple qubits are considered together. 2 classical bits can be in any of 4 configurations. 2 qubits, in contrast, can occupy superpositions of all 4 basic configurations at once, with amplitudes assigned to each. The space of possible states grows rapidly with the number of qubits. For 3 qubits, there are 8 basic configurations. For 4 qubits, there are 16, and in general, the number doubles with each added qubit. A system of many qubits can therefore exist in an extremely complex superposition that encodes information in subtle correlations among its parts. This structure is not visible in a single measurement outcome, which always yields one definite string of results, but it influences the probabilities for those outcomes in ways that can be shaped by careful design of the sequence of operations applied to the system. It is important to distinguish this quantum superposition from a simple statistical mixture. A statistical mixture arises when a system is in one of several possible states each, with a certain probability, but no deeper coherence links the alternatives. For example, a box containing coins where some are known to be heads and some tails, is described by a distribution over definite states. A quantum superposition, by contrast, describes a single system whose components of state can interfere. Experiments can be devised that distinguish these 2 situations. In particular, when coherent operations are applied to a superposition and then reversed interference can restore certain features that would be washed out in a mixture. This difference is crucial for quantum computation, where algorithms often rely on the ability of superposed components to interfere constructively for some outcomes and destructively for others, thereby changing the distribution of measurement results in a way that highlights the desired answer. The superposition principle is therefore not only a curious trait of microscopic systems, but a resource that can be exploited. The presence of superposition raises further questions about how to visualize what a quantum system is doing between measurements. In classical mechanics, a clear picture is available, at least in principle. A particle follows a trajectory through space, and at any given time it has a definite position and momentum. In quantum mechanics, that picture is replaced by a state that spreads over many possibilities. Assigning definite values simultaneously to certain pairs of quantities leads to contradictions with observed interference effects. The mathematics of the theory encodes this through operator relationships and uncertainty relations, which limit how sharply certain properties can be defined together. From a practical standpoint, physicists often set aside detailed visualizations and work directly with the abstract state descriptions, trusting that the formalism, when correctly applied, will yield predictions that match experiment. In the background, however, the question remains of what, if anything, the superposition corresponds to in more familiar terms. For the development of quantum technologies, the operational meaning of these ideas is what matters most. In laboratories, building quantum devices, researchers devote significant effort to preparing qubits in well-defined superposed states, protecting those states from unwanted interactions with the environment and implementing sequences of operations that take advantage of coherence. Any uncontrolled coupling to surrounding degrees of freedom can quickly transform a delicate superposition into a statistical mixture, a process known as decoherence. When that happens, the specifically quantum advantages of the device are lost. Understanding superposition not only as a concept in the equations, but as a physical condition that can be created, maintained, and destroyed, becomes a central practical concern. The same property that leads to puzzling interpretations in foundational discussions is what gives quantum systems their distinctive power when harnessed in engineered settings. Thus, the qubit, simple in definition yet rich in behavior, serves as a bridge between the abstract structure of quantum theory and its concrete use in information processing. It demonstrates how a system with only two measurement outcomes can nonetheless inhabit a continuous space of possible states, how probability in quantum mechanics is tied to amplitudes that can interfere, and how control of superposition opens paths to new forms of computation and communication. This understanding prepares the ground for examining experiments in which single quanta, such as individual electrons or photons, display interference patterns that defy classical expectations, and for exploring how these patterns lead to further questions about the nature of reality at its most basic level. Among the many experiments that display quantum behavior, one particular arrangement occupies a central place because it combines simple equipment with highly non-classical results. This is the double-slit experiment. Its components are easy to describe in ordinary language. There is a source that emits particles, a barrier, with two narrow openings and a screen or detector that records where the particles arrive. The particles can be electrons, photons, neutrons, or even larger objects under suitable conditions. The essential structure remains the same. A stream of particles is sent toward the barrier. Some particles pass through the slits and eventually reach the screen, where they leave marks that can be counted and mapped. The question is how this pattern of marks depends on the arrangement of slits and on the nature of the particles. In a classical picture, particles are treated as small localized objects that follow trajectories. A single slit in the barrier simply blocks most paths and allows a beam to pass through a narrow opening. On the screen behind the slit, the distribution of impacts forms a broad band, reflecting the fact that particles passing through the opening can be deflected by small angles. If there are two slits open separated by some distance, it is natural to expect that the pattern on the screen will be the sum of two such bands. Each particle would pass through either the left slit or the right slit, and the total distribution would be a simple overlay of the contributions from each path. Where one slit alone would give a bright region of impacts, two slits should give two overlapping bright regions. The central idea is straightforward. Each particle chooses a route, and the screen counts how many came through each opening. When this expectation is tested, however, the observed pattern is different. When both slits are open and the incoming particles are prepared and detected under conditions where quantum effects are important, the screen shows a series of alternating bright and dark regions. There are bands where many particles arrive, separated by bands where very few or almost none are detected. This pattern is known as an interference pattern. It resembles the distribution created on a screen by water waves or light waves passing through two openings. The bright regions correspond to places where wave crests from the two slits reinforce each other. The dark regions correspond to places where a crest from one slit coincides with a trough from the other, canceling the disturbance. In the wave picture, each slit acts as a new source of waves, and the overlapping waves on the screen create a pattern of reinforcement and cancellation that varies with position. For classical waves, the appearance of such a pattern is expected and is well understood. For localized particles traveling along definite paths, it is not. The tension can be sharpened by considering what happens when the intensity of the source is reduced so far that only one particle at a time travels through the apparatus. In such runs, the detector records isolated events, single dots appearing one by one on the screen. Each event is a localized impact, as if a small object hit the surface at that point. There is no sign in any individual detection of a wave extended over space. Yet as the events accumulate over many repetitions, the familiar interference pattern gradually appears. The bright bands fill in more quickly, the dark bands remain sparsely populated. The final distribution matches the pattern produced when many particles are sent through at once. The experiment therefore shows that the interference pattern is not a product of particles colliding or interacting with each other on the way. It emerges even in the regime where the particles pass through the apparatus singly. The quantum description accounts for this by associating a wave function or state amplitude with each particle. This wave function evolves according to a linear equation. At the barrier with its two slits, the part of the wave function that reaches one opening and the part that reaches the other both contribute to the amplitude at any point on the screen. The resulting probability for detection at a given location is derived from the squared magnitude of the sum of these contributions. Because amplitudes, unlike simple probabilities, can interfere, there are positions where the contributions combine to give a large probability and positions where they cancel, leading to a small probability. The pattern of bright and dark regions is thus traced back to the structure of the wave function and to the superposition principle that allows amplitudes from different paths to add coherently. If one slit is closed, the corresponding contribution is removed. The pattern on the screen changes and the interference structure disappears. The result is a single broad distribution, similar to what the classical intuition suggests. This sensitivity to the availability of alternative paths is one of the defining features of the quantum world. The experiment indicates that when both slits are open, the description of the particle must involve both possibilities, not in the sense that the particle takes one route or the other unknown to observers, but in the sense that the full quantum state includes contributions from both paths that cannot be ignored. Attempts to refine the description in classical terms lead to difficulties. One might wish to say that each particle still goes through one slit only unknown to the experimenter, and that the interference pattern arises from some hidden arrangement in the source. However, careful variations of the setup rule out simple versions of this idea. For instance, if a detector is placed at the slits to record which path each particle follows, the interference pattern is lost. The distribution on the screen changes to one that matches the sum of two single slit patterns. The act of acquiring which path information alters the outcome. It is not merely that the observer learned something that was already true. The conditions that allow interference are themselves changed. More refined theoretical analyses and experiments extend this conclusion. Configurations can be designed where partial information about the path leads to partial loss of interference in a way that smoothly interpolates between the two extremes. These results show that the interference pattern is not compatible with a model in which particles always carry definite, which slit labels that can be revealed without affecting the rest of the motion. The double-slit experiment has been performed with many kinds of particles and with increasingly sophisticated detectors. Electrons, neutrons, atoms, and even complex molecules have displayed interference patterns when cooled, isolated, and sent through slits under suitable conditions. In each case, the same logic applies. When the paths are indistinguishable in the relevant sense, interference appears. When the apparatus is modified to mark or to distinguish the paths, interference fades. The scale of the objects involved does not alter the underlying principles. What changes is how difficult it becomes to maintain the necessary isolation from environmental disturbances. As the systems increase in size and complexity, interactions with surrounding air light and internal degrees of freedom tend to destroy coherence, rapidly washing out interference and leaving only classical-like mixtures. This practical limitation explains why interference effects are so familiar for light and electrons in controlled experiments, but not for everyday objects. There is no evidence, however, of a sharp boundary where the rules switch from quantum to classical. The same formalism applies. Only the effectiveness of decoherence changes. The way many physicists now organize their thinking about the double-slit experiment is shaped by the path integral formulation introduced in the mid-20th century. In this approach to compute the probability of a particle arriving at a certain point on the screen, one conceptually sums contributions from all possible paths that connect the source to that point. Each path is assigned a complex amplitude whose phase depends on the action along the path, a quantity built from energy and time. The total amplitude at the point is the sum of all these contributions, and the probability is obtained from the squared magnitude of this sum. For regions where nearby paths contribute amplitudes that are nearly in phase, constructive interference boosts the probability. For regions where phases vary rapidly and contributions cancel, the probability is suppressed. When both slits are open paths, passing through both openings contribute. When one slit is closed, a whole family of paths is removed and the pattern changes. The path integral framework does not rely on a choice between thinking of the particle as a tiny object or as a wave. It treats the sum over paths as a calculational rule that yields correct predictions. The question of what, if anything, the individual paths correspond to physically is left open. Some interpretations take the paths as a mathematical tool, avoiding further claims. Others suggest that the particle, in some generalized sense, really explores all allowed routes. The double-slit experiment lies at the heart of these discussions because it presents a clear case where classical notions of trajectory fail to match observed behavior. Yet the experimental arrangement remains conceptually simple. The experiment also illustrates how quantum mechanics combines simplicity and depth. The apparatus can be drawn with a few lines. The underlying mathematics in suitable formulations boils down to rules for assigning and adding complex numbers. The resulting interference patterns are striking and reproducible. At the same time, the implications for how physical processes unfold between preparation and detection continue to be debated. The double-slit experiment shows that nature does not conform to a picture in which particles always follow single definite paths, while a separate wave guides probabilities in the background. Instead, the observed patterns suggest that the quantum state itself, with its capacity to form superpositions of different histories, plays a central role in determining what is seen. This realization sets the stage for further exploration of how quantum systems behave when more particles are involved, when correlations between distant systems are established, and when attempts are made to store and process information in large assemblies of controlled quantum units. The path integral view offers a careful way of organizing the idea that every possible route from source to detector contributes to the final outcome in a quantum process. Instead of asking which path a particle actually takes, this formulation asks how each conceivable path enters a calculation of probabilities. For a given experimental setup, such as the double-slit arrangement, one identifies all the paths that start at the emission point and end at a point on the screen. To each path, the formalism assigns a complex number called an amplitude. A complex number can be pictured as a point in a plane or as a hand on a clock face with a certain length and a certain angle. The length is related to how strongly that path contributes. The angle or phase encodes how the contribution lines up or fails to line up with contributions from other paths. The total amplitude at the point on the screen is obtained by adding all these little clock hands tip to tail. The probability of detecting the particle at that point is given by the squared length of the resulting sum. This rule is simple to state, but has far-reaching consequences. In regions where many nearby paths contribute amplitudes with similar phases, the clock hands tend to point in nearly the same direction. Their sum has a large length, and the probability is high. In regions where the phases vary rapidly, the hands point in many directions and cancel each other partly or almost completely. The resulting sum is small, and the probability is low. This visual picture captures how interference emerges from the structure of the amplitudes. Opening or closing a slit changes which families of paths are allowed. With both slits open, there are paths passing through the left slit and paths passing through the right slit, each set carrying its pattern of phases. Their combined contributions at the screen produce the characteristic bright and dark bands. Closing one slit removes a whole collection of clock hands from the sum, changing the pattern of reinforcement and cancellation. The mathematics does not require a decision about whether the particle is really a wave or a tiny object following a single route. It only requires that all allowed paths be included in the sum. This approach can be applied beyond the simple geometry of slits and screens. For any system that can be described in terms of positions and times, one can consider the set of all possible histories and assign an amplitude to each. The rule for constructing these amplitudes involves a quantity called the action built from the energy of the system and the time evolution. In the classical limit, where many contributions combine in such a way that phases change very rapidly away from the path of stationary action, the sum is dominated by paths near the classical trajectory. In that regime, the familiar laws of motion emerge as approximations. The particle appears to follow a single path, because contributions from wildly different routes largely cancel each other out. The classical world is thus recovered as a regime in which interference sharply favors certain histories. In diagrams and calculations, this transition from many paths to a single effective path can be tracked explicitly. The path integral view also sharpens the sense in which probabilities in quantum mechanics are different from probabilities in classical theories. In classical statistical models, probabilities are assigned to whole trajectories or configurations that could, in principle, exist independently of observation. One might imagine a particle that really takes one well-defined path, while the probability distribution expresses ignorance about which one. In the quantum path integral, by contrast, the amplitudes associated with different paths can interfere. This interference is essential to reproduce observed phenomena, such as the double-slit pattern. If one tried to interpret the whole construction simply as a probability distribution over definite paths, the interference terms would have no place. Taking the squared magnitude after summing amplitudes rather than summing squared magnitudes is a key feature. It means that the paths do not merely compete, they also cooperate or cancel in ways that have no classical counterpart. One of the intriguing aspects of this formulation is that, at least in principle, every path that connects the initial and final events contributes not only the most direct or smooth paths. Even wildly indirect routes in which the particle seems to wander far from the straight line are assigned amplitudes. For realistic systems, many of these contributions cancel because their phases vary rapidly. However, the idea remains that the calculation recognizes the existence of a vast space of hypothetical histories. In thought experiments, this can be extended to paths that stray over large distances before returning. In practice, their contributions are negligible, but their presence in the formalism underscores how different the quantum picture is from a simple story, in which a particle chooses one neat trajectory. The amplitude for arriving at a point is not associated with a single storyline, but with an aggregate of all possible ones. The use of complex numbers and phases can seem abstract, but it has practical advantages. The rules for adding amplitudes obey simple linear relations. When systems are combined, their joint amplitudes are formed by straightforward products and sums. This makes it possible to treat complicated arrangements of beams, slits, lenses, and detectors within a unified framework. It also allows clear connections to be made between the behavior of particles and the behavior of classical waves. In many contexts, quantum amplitudes can be seen as generalizations of wave fields. Interference patterns, diffraction, and other wave-like phenomena emerge naturally. At the same time, the formalism extends beyond systems that have obvious wave analogies. It provides a common language for processes in atomic physics, nuclear physics, and high-energy collisions. For example, when analyzing scattering experiments in which particles collide and produce other particles, the path integral viewpoint helps organize contributions from many different possible interaction histories. In such cases, diagrams can be drawn that represent classes of paths where particles emit and absorb other quanta in various sequences. Each diagram corresponds to a mathematical expression for an amplitude. Summing these contributions gives the total amplitude for a given process. The probabilities derived from these amplitudes match cross-sections measured in accelerators. The visible tracks left in detectors arise from individual events, but the distribution of many events reflects the underlying amplitude structure. Although the technical details go far beyond the double-slit experiment, the core idea remains the same. Probabilities are obtained by squaring the modulus of a sum over complex contributions from possible histories. The question of interpretation reappears in this setting. Some physicists regard the path integral as a powerful computational device that should not be taken literally beyond its role as a recipe. From this perspective, the sum over paths is a convenient mathematical construction, and asking which paths the particle really follows is considered an ill-posed question. Others are inclined to treat the multitude of paths as representing something more concrete about the way quantum systems evolve, even if that picture cannot be translated directly into classical language. In either case, the formalism forces a departure from the idea that a single well-defined trajectory can be assigned to a quantum particle, independent of how it is measured. The experimental evidence from interference and related phenomena supports the view that the full set of possible alternatives plays a role in shaping observed outcomes. The path integral formulation also suggests new ways of thinking about complex systems where many degrees of freedom interact. In such cases, the number of possible paths grows enormously. Each component of the system can follow many routes, and their combined histories form an intricate network. The amplitudes assigned to these collective paths encode interference patterns not only in space and time, but also in internal configuration space. In principle, the behavior of a molecule, a crystal, or even a macroscopic object could be described in this way. In practice, the sheer number of paths makes direct calculation impossible for large systems. Instead, approximations and effective theories are used, yet the underlying principle remains that the quantum description involves contributions from a vast ensemble of alternatives. When systems become large and interact strongly with their environment, interference between macroscopically distinct paths is suppressed by decoherence, and classical explanations become adequate. Nevertheless, the foundation remains quantum. An interesting connection arises when this way of thinking is applied to information processing. In a quantum computer, a register of qubits is manipulated so that its joint state explores a large space of possible configurations. At each step, logical operations correspond to transformations of amplitudes. The path integral picture provides one way to visualize how an algorithm guides the flow of amplitudes through this space. Certain paths in the computational history interfere constructively toward outcomes that encode the solution to a problem, while other paths interfere destructively and reduce the weight of irrelevant outcomes. The algorithm does not enumerate each possible classical configuration in turn. Instead, It arranges for the amplitudes over many configurations to interact in parallel. The final measurement still yields a single classical result, but the distribution of possible results has been shaped by interference in a way that classical procedures cannot easily mimic. This possibility motivates intense efforts to build and control systems where coherent superpositions of many paths in configuration space can be sustained for long enough to perform useful computations. The conceptual step taken by the path integral formalism is to treat the space of possibilities as basics. Instead of asking what a single particle is doing at each instant in a narrow sense, the theory assigns a structured collection of amplitudes to all ways that process could unfold. Observed probabilities emerge from the squared magnitude of sums of these amplitudes. The simplicity of the rules contrasts with the difficulty of fitting them into everyday intuitions derived from classical motion. In the classical world, it seems natural to imagine that there is a definite answer to questions such as which route a particle took or which slit it passed through, even if that answer is inaccessible. Quantum experiments show that insisting on such answers leads to conflicts with the observed interference patterns. The path integral offers a way to give up that insistence while maintaining predictive power. It describes a world in which possibilities are not merely hypothetical labels attached from outside, but active components in the structure of physical law. This view will prove especially important when considering systems of more than one particle, where correlations between distant outcomes reveal further departures from classical expectations, and where the concept of a single history for each subsystem becomes even harder to maintain. When more than one quantum system is considered at the same time, new structures appear that have no counterpart in classical physics. Among these, entanglement is the most distinctive. It describes a situation in which the properties of two or more particles are linked so that the state of the whole cannot be written as a simple combination of states for each part. The systems form a single joint object in the mathematical description even when they are later separated in space. Measurements made on one part are then correlated with measurements made on the other in ways that cannot be reproduced by any model in which each particle simply carries its own set of pre-existing values. Spin again provides a clear setting for discussing this phenomenon. Imagine a source that produces pairs of electrons in such a way that their total spin in some direction is constrained. One simple arrangement gives pairs where, when the spins are later measured along the same axis, one result is always up and the other is always down. No matter how the pairs are oriented in space, if both spins are measured along an agreed axis, the outcomes are always opposite. Quantum mechanics describes this situation with a particular joint state often introduced as a superposition of two possibilities, one where the first electron is up and the second is down, and one where the first is down and the second is up. The two contributions are combined with equal weight and with a specific relative phase. The result is not a mixture in which some pairs are actually in one configuration and some in the other. It is a single state in which neither electron has an individual spin assignment before measurement, but the pair as a whole has a definite total property. To see the difference, consider what happens when each electron is sent in a different direction, one perhaps toward a detector on Earth, and one toward a detector placed far away. Before any measurement is made, the joint state is still entangled. No individual spin value can be assigned to either electron, but there is a precise guarantee about the relation between their outcomes. If an experimenter measures the spin of the first electron along some chosen axis and finds it to be up, quantum mechanics predicts that a measurement along the same axis on the second electron will yield down with certainty. If the first result is down, the second will be up. The theory also predicts how often different pairs of results will appear if the experimenters choose different measurement axes. The key is that these joint probabilities obey characteristic patterns that differ from any model in which each electron carried a fixed table of answers for all possible measurement directions. This observation lies at the heart of the argument developed in the 1930s by Einstein, Podolsky, and Rosen, and later sharpened in different terms by others. They were concerned about whether the quantum description could be regarded as complete. If a measurement on one particle allows instant inference of the outcome of a similar measurement on a distant partner, they argued, then either the first measurement somehow influences the distant particle faster than any signal could travel, or else the distant particle already had a definite value that the quantum state failed to represent. They found both options troubling and suggested that the theory might be incomplete, missing additional variables that would restore a more classical picture of separate objects with well-defined properties. For some time, this question remained largely philosophical because it was not clear how to design an experiment that could distinguish between the standard quantum predictions and those of a hypothetical theory, with hidden variables that also respected reasonable constraints such as locality. Locality in this context is the idea that influences cannot propagate faster than a certain speed often associated with the speed of light. In the 1960s, Bell provided a way forward. He derived inequalities that any local hidden variable theory must satisfy in the statistics of correlated measurements on separated systems. These inequalities place bounds on certain combinations of correlations. Quantum mechanics predicts that for appropriately chosen measurement directions, these bounds are exceeded. The difference is not in single outcomes, which remain individually random, but in the pattern of joint outcomes across many trials. Experiments have since been performed in which pairs of entangled photons or other particles are emitted and detected at locations sufficiently far apart that no signal traveling at or below the speed of light could connect the measurement events in time. The orientation of the measurement devices is varied so that different combinations of settings can be sampled. The recorded correlations are then used to test the inequalities. Over the decades, experimental groups have refined their apparatus to close various loopholes, such as the possibility that the sample of detected pairs is biased, or that the choice of measurement setting might be influenced by unnoticed common causes. The accumulated results support the quantum predictions and violate the inequalities that any local hidden variable model would need to respect. These findings do not suggest that communication faster than light is possible. The outcome at each detector remains random when viewed on its own. No experimenter can control whether a particular run yields up or down for a given particle. What the entangled state ensures is that when results from both sides are later compared, they exhibit correlations that cannot be explained by any scheme in which each particle simply carried pre-assigned answers that are revealed at measurement. The statistical structure of the outcomes is such that it requires either abandoning locality in the strict sense used in the derivation of the inequalities or revising the classical idea that physical properties must have definite values before measurement. Different interpretations of quantum mechanics resolve this tension in different ways, but they all must accommodate the robust experimental fact that entangled systems behave in a way that cannot be captured by simple, local realist pictures. Entanglement, therefore, represents a stronger kind of correlation than is familiar from everyday experience. In a classical setting, correlations can be explained by common causes. If two coins are prepared in a certain way and then separated, one might know in advance that they always show opposite faces when revealed. Each coin carries its own value, and the joint pattern reflects shared preparation. In the quantum case, by contrast, entangled systems can display correlations between outcomes in different measurement bases, not just in a single fixed basis. No assignment of pre-existing values can reproduce all of these patterns if locality is maintained. The entangled state encodes a web of potential correlations that become actual only when measurements are made, yet the structure of those correlations is already fixed by the state. From a practical standpoint, entanglement is not only a conceptual challenge, but also a resource. In quantum information, science-entangled pairs of qubits are used as building blocks for tasks such as quantum teleportation, superdense coding, and certain secure communication protocols. In these applications, the non-classical correlations between entangled systems allow information to be processed and shared in ways that cannot be achieved by classical means alone. For example, quantum teleportation uses an entangled pair shared between two locations together with classical communication to transfer an unknown quantum state from one qubit to another without physically sending the original system. The procedure does not enable faster-than-light transfer of usable signals, but it shows how entanglement can be used to restructure where and how quantum information is stored. The presence of entanglement also affects how measurements on composite systems are understood. When two qubits are entangled, measuring one qubit in a particular basis does more than merely reveal a pre-existing value. It changes the joint state in such a way that the possible outcomes for later measurements on the second qubit are updated. This process can be described precisely with the standard rules of quantum mechanics. The collapse of the state upon measurement is not represented as a physical signal propagating between the qubits at finite speed. Instead, it is treated as an update of the description used by the theory to connect preparations and outcomes. The question of whether there is any deeper mechanism behind this update remains open to interpretation. Some approaches treat the collapse rule as a pragmatic tool that captures how experimental knowledge changes, while others seek a more detailed dynamical account. In many body systems, entanglement can become extremely complex. Instead of simple pairs, one can consider chains, lattices, or networks of particles whose joint state cannot be decomposed into independent parts. The pattern of entanglement across a system influences its thermal properties, its phase transitions, and its response to external probes. In certain phases of matter, long-range entanglement plays a central role in defining the global characteristics of the system, such as in topological states that are robust against local disturbances. Understanding and classifying these patterns is an active area of research. The same mathematical tools that describe entanglement in simple spin pairs are being extended to large assemblies of qubits in quantum simulators and early quantum processors. The recognition that entanglement is both real and exploitable has reshaped the view of quantum mechanics. What was once regarded mainly as a source of paradoxes is now seen as a structural feature of the theory that enables technologies beyond the reach of classical designs. At the same time, the underlying questions that prompted the original debates have not disappeared. The experiments that violate Bell-type inequalities make it difficult to hold on to all the intuitions derived from classical locality and realism at once. One can maintain a form of locality, but accept that measurement outcomes do not correspond to pre-existing values, or one can keep a richer notion of realism at the cost of introducing non-local influences at the level of the hidden description. There is no consensus on which route, if any, provides the best conceptual picture. What is clear is that entanglement forces a revision of how composite systems are imagined. In a classical framework, a pair of objects is fully described by specifying the state of each object separately and perhaps adding some statistical correlation. In the quantum framework, there exist joint states that cannot be written in this way. The whole is not just the sum of its parts. Instead, the parts derive some of their physical character from the state of the whole. This conclusion is not based on speculation, but on precise experiments carried out over many years. It shows that the structure of reality at the quantum level is more tightly connected than classical intuitions would suggest, and it prepares the ground for discussions of how such strongly correlated systems can be controlled and used in the design of quantum computer sensors and communication networks, where entanglement is not an oddity to be avoided, but a central ingredient to be engineered. In the study of quantum information, the abstract ideas of superposition and entanglement take on a concrete role as building blocks for new kinds of machines. A single qubit, as already described, can exist in a superposition of two basic states. When more qubits are combined, the space of possible states expands very rapidly. 2 classical bits can be in any of 4 configurations, 3 can be in any of 8, and in general, the number of possible classical configurations doubles with each additional bit. A classical machine that wishes to examine each configuration separately must, in effect, step through this list one by one or manage it with clever shortcuts. In a quantum device, by contrast, a collection of qubits can be prepared in a state that is a superposition of many or even all of these configurations at once. The full state of the system is specified by a set of complex amplitudes, one for each basic configuration. For a few qubits, this set is easily written down. For 10 qubits, there are already 1,024 amplitudes. For 20 qubits, there are more than 1,000,000. For 100 qubits, the number of amplitudes required to describe a completely general state is 2 raised to the power of 100, an enormous figure that far exceeds what can be stored explicitly in the memory of any existing classical computer. If one imagines scaling further to a few hundred qubits, the number of amplitudes required to describe the most general state grows beyond the estimated number of atoms in the observable universe, yet the quantum system itself does not keep track of these amplitudes one by one in any conventional sense. It simply evolves according to the linear equations of the theory. The aim of quantum computing is to engineer physical systems whose natural evolution carries out useful transformations in this vast space without ever listing its contents explicitly. From this perspective, a quantum computer is a device that manipulates the amplitude distribution over all possible bit strings in a controlled way. Logical operations, known as gates, act on one or more qubits at a time and correspond to unitary transformations that preserve the overall structure of the state. By designing sequences of such gates known as circuits, one can guide how amplitudes flow between configurations. The goal of many quantum algorithms is to arrange these flows so that at the end of the computation, the amplitude associated with the correct answer is large and the amplitudes of incorrect answers are suppressed. A final measurement of the qubits then yields the desired result with high probability. This way of working is very different from a classical computation. In a classical machine, operations transform definite bit strings into other definite bit strings. At each step, the machine has a well-defined configuration. In a quantum machine, at least in the idealized picture, the register is in a superposition of many bit strings. Each gate acts simultaneously on all components of this superposition, altering the pattern of amplitudes. The computation is therefore parallel in a sense that has no direct classical analog. It is not that many separate classical computations run side by side. Rather, a single quantum evolution restructures the entire superposed state in one process. The advantage becomes apparent in problems where the structure of the solution allows amplitude contributions from many different paths through this state space to interfere constructively for the correct answer while interfering destructively for incorrect ones. The most cited early examples include algorithms for factoring large numbers and for searching unsorted databases faster than classical methods. In these cases, the quantum algorithm does not guarantee success in every attempt, but it changes the scaling of resources needed as the size of the problem grows. To explore these ideas in practice, researchers build physical qubits in diverse platforms. Some qubits are realized as trapped ions, where the internal energy levels of individual ions serve as the two basis states, and laser pulses implement gates. Others use superconducting circuits cooled to very low temperatures where quantized energy levels in microwave resonators or Josephson junction devices act as qubits and are controlled by precisely timed electrical signals. Photonic qubits encode information in the polarization or path of single photons manipulated by optical components. Solid-state defects, such as specific arrangements of atoms in a crystal lattice, can also host qubits with long coherence times under suitable conditions. Each approach has strengths and weaknesses involving trade-offs between gate speeds, error rates, ease of scaling, and integration with existing technologies. A central difficulty in all these architectures is maintaining coherence. The delicate superposed and entangled states needed for quantum computation are highly sensitive to interactions with their environment. Random fluctuations in electromagnetic fields, vibrations, stray photons, and other sources of noise can disturb the phase relations between amplitudes, gradually converting a pure quantum state into a statistical mixture. This process, known as decoherence, erases the interference effects that algorithms rely on and causes quantum devices to behave more like classical probabilistic machines. To combat decoherence, experimental setups isolate qubits as much as possible, operate them at low temperatures, and use error correction schemes that distribute logical information across multiple physical qubits. Quantum error correction encodes a single logical qubit into a carefully entangled state of many physical qubits in such a way that certain patterns of errors can be detected and corrected without directly measuring and collapsing the logical information. Implementing these protocols requires additional qubits and operations, increasing the complexity of the hardware. Despite these challenges, progress has been steady. Small quantum processors with tens or low hundreds of qubits have been built and operated by research groups and companies around the world. These devices are not yet capable of solving practical problems faster than the best classical algorithms for general tasks, but they provide test beds for studying noise, implementing simple algorithms, and exploring the transition from small quantum systems that can still be simulated classically to larger ones that cannot. Experiments have demonstrated controlled entanglement among many qubits, basic forms of error correction, and limited forms of quantum simulation in which the behavior of one quantum system is emulated by another, more easily controlled one. The current era is sometimes described as one of noisy intermediate-scale quantum devices, reflecting both the modest number of qubits and the presence of significant imperfections. Even at this stage, the conceptual implications are notable. A device with a few dozen well-controlled qubits is already operating in a domain where direct classical simulation becomes demanding. For some specially chosen circuits, measuring certain properties of the output distribution may be practically intractable for classical supercomputers, while the quantum device can produce samples straightforwardly as part of its natural operation. These demonstrations do not yet translate into immediate everyday applications, but they offer evidence that the exponential growth of configuration space in multi-qubit systems is more than a theoretical curiosity. It is a resource that can be touched experimentally. The question then shifts from whether such systems can outpace classical computation in principle to how reliably and usefully they can be controlled in practice. The potential reach of quantum computers extends beyond speedups for particular tasks. Because the state space of many qubits mirrors the state spaces of other quantum systems, carefully engineered quantum devices can act as simulators for materials, molecules, and field theories that are difficult to study directly. Instead of solving the equations of motion for a complex quantum system using classical approximations, one can, in principle, program a quantum simulator to adopt the same Hamiltonian or effective energy operator and then observe its behavior. This approach could shed light on high-temperature superconductivity quantum phase transitions and the dynamics of strongly correlated electrons in ways that complement classical numerical methods. Again, the key is that the simulator naturally occupies and explores the same exponentially large configuration space as the system being modeled rather than trying to represent that space indirectly. At the same time, it is important to recognize limits. Quantum computers do not offer universal shortcuts for all computational problems. There are tasks for which no significant quantum advantage is known, and there are fundamental constraints on what any physical device can achieve. The presence of quantum parallelism and interference does not override these constraints. It alters the landscape, opening some paths that classical machines cannot follow efficiently, while leaving others essentially unchanged. Ongoing research aims to map this landscape, more precisely identifying which problems are well suited to quantum acceleration and which are not. Cryptography optimization, machine learning, and chemical simulation are all areas where quantum methods are being investigated with varying degrees of promise. As this work continues, the relation between the abstract mathematics of Hilbert spaces and amplitudes and the practical engineering of devices remains central. The theory says that a register of qubits resides in a vector space whose dimension grows exponentially with the number of qubits. The device builder sees hardware arranged on a chip or in a vacuum chamber with control lines, lasers, and amplifiers. The challenge is to ensure that the physical system remains a faithful realization of the ideal qubits and gates the theory describes. Imperfections, cross-talk, and drift can all cause the actual evolution to deviate from the intended circuits. Careful calibration error, mitigation, and system design are therefore as significant as the design of algorithms. The picture that emerges is one in which quantum computers are not magic solutions, but carefully constructed platforms that attempt to exploit the structure of quantum mechanics as fully as possible. The same principles that make the double-slit experiment so striking and that make entangled spins so counterintuitive now appear as tools to be harnessed. Superposition allows many configurations to be present at once in a controlled way. Entanglement ties the behavior of qubits together so that operations on one part of the system have structured effects on the whole. Interference lets certain computational paths reinforce and others cancel. All of these features are fragile and must be protected against noise. When they are present, they open access to computational processes that have no direct analog in classical physics. When they are lost, the device reverts to more ordinary behavior. The ongoing effort to build scalable quantum computers is thus both a technological and a conceptual exploration of how far the uniquely quantum aspects of reality can be pushed into the macroscopic world of instruments and applications. The abstract features of quantum mechanics, such as superposition and entanglement, might at first seem removed from ordinary experience, confined to carefully controlled experiments and to proposed future computers. In reality, quantum effects already lie at the heart of many technologies that operate quietly in the background of daily life. Some of these devices were developed before the quantum theory was fully understood, but their functioning is now described and refined using the modern framework. Others have been designed explicitly to exploit delicate quantum properties. Taken together, they show that the strange behavior discussed in theoretical lectures has direct consequences in practical instruments. One of the clearest examples is the atomic clock. Timekeeping has always depended on regular physical processes, from the swing of pendulums to the vibration of quartz crystals. Atomic clocks use transitions between energy levels in atoms as their reference. In quantum mechanics, an atom has discrete energy levels. When it moves from one level to another, it absorbs or emits radiation with a very specific frequency. By locking an electronic oscillator to this frequency, an atomic clock achieves remarkable stability. The best modern clocks use atoms such as cesium or optical transitions in ions and can keep time so precisely that they would lose or gain less than a second over periods comparable to the age of the universe. This precision is not an incidental detail. Global navigation systems rely on synchronized atomic clocks on satellites to determine positions on Earth. Small relativistic effects due to the satellite's motion and altitude must be corrected, and the underlying timing is guaranteed by quantum transitions. In this sense, standing in a location determined by a satellite navigation receiver is already an indirect interaction with quantum physics. Quantum behavior also appears in many sensors that measure fields, rotations, or accelerations with high sensitivity. Superconducting quantum interference devices are an example. They use loops of superconducting material interrupted by weak links. In a superconductor, electrons form pairs that behave collectively as a quantum state described by a single phase across the material. When such a loop is exposed to a magnetic field, the phase difference around the loop is constrained in a way that makes the device respond with oscillatory changes in its electrical properties. This allows extremely small magnetic fields to be detected. Other quantum sensors use ensembles of atoms whose spins precess in magnetic fields with their collective response read out optically. By preparing these atoms in carefully chosen states and by minimizing noise, experimenters can measure variations in the field caused by currents in the brain, by geological structures, or by distant storms. Again, the sensitivity arises because quantum coherence and discrete energy levels produce sharp, well-defined responses. Optical technologies also draw heavily on quantum ideas. Lasers, for example, operate by creating a population of atoms or molecules in excited states and stimulating them to emit photons in phase with one another. The resulting coherent beam has a narrow frequency spread and well-controlled direction. Although lasers are now common in communications, manufacturing, and medicine, their operation is rooted in quantum descriptions of emission and absorption. More advanced optical systems use single photons as carriers of information. In quantum key distribution, for instance, pairs of parties share a secret cryptographic key by sending quantum states of light through a channel. The protocol is designed so that any attempt at eavesdropping inevitably disturbs the quantum states in a detectable way because unknown quantum states cannot be copied perfectly, and certain measurement choices are incompatible. This does not make communications unbreakable in a general sense, since practical vulnerabilities remain, but it does show how specifically quantum principles can underpin new security schemes. Quantum effects also play a role in the design of materials and devices for electronics. The operation of transistors, which control current flow in nearly all modern circuitry, depends on quantum tunneling and on the band structure of solids. In a crystal lattice, electrons occupy bands of allowed energies separated by gaps. Whether a material behaves as a conductor, an insulator, or a semiconductor depends on how these bands are filled. By doping semiconductors and by layering different materials, engineers control quantum states of electrons in ways that enable switches, diodes, light, emitting devices, and detectors. Although everyday users interact only with the macroscopic performance of phones, computers, and sensors, the underlying design rests on quantum interpretations of how electrons move and how they interact with electromagnetic fields in confined geometries. In more recent developments, researchers are building devices that maintain entanglement and superposition across longer times and distances. Quantum communication experiments have demonstrated entangled photon pairs distributed between ground stations and satellites. The correlations in polarization measurements between widely separated detectors match the predictions of entangled states. These demonstrations extend the Bell test experiments discussed earlier into regimes where one detector or both may be on moving platforms, showing that entanglement is robust across changing reference frames. In parallel prototype quantum networks, link small quantum processors or memory nodes with optical fibers, using photons as carriers of entanglement between distant nodes. These systems are at an early stage, limited in scale and reliability, but they show how entanglement can serve as a resource in extended architectures rather than only in local laboratory setups. Quantum simulators provide another example of quantum theory turned into a tool. In these devices, arrays of ultra-cold atoms are trapped in optical lattices formed by intersecting laser beams. The atoms, cooled to temperatures close to absolute zero, occupy well-defined quantum states and interact with neighbors according to tunable rules. By adjusting the depth and spacing of the potential wells formed by the lasers and by controlling the interactions between atoms, experimenters can create systems that mimic the behavior of electrons in solids, spins on a lattice, or particles in model field theories. Observing how these controlled quantum systems evolve in time or respond to changes in parameters provides insight into phenomena that are difficult to calculate classically. Once again, the essential quantum features are not incidental. The simulations rely on superposition and entanglement in the simulator to reflect the superposition and entanglement in the system being modeled. Even in fields such as metrology and geophysics, quantum ideas guide the design of instruments. Atom interferometers, in which matter waves split and recombine in configurations analogous to optical interferometers, can measure accelerations and rotations with high precision. In these instruments, an ensemble of atoms is put into a superposition of two paths that experience slightly different gravitational or inertial effects. When the paths are recombined, interference in the resulting state shifts depending on the difference in phase accumulated along the two routes. Measuring this shift reveals minute changes in gravitational fields or in motion. Such devices have been used to measure variations in local gravity due to underground structures and are proposed for tests of fundamental physics. The practical benefit is that quantum coherences among many atoms can enhance sensitivity beyond what would be achievable with classical test masses alone. In parallel with these more specialized instruments, early quantum processors are being made available through cloud-based platforms. Users can submit circuits to run on small quantum chips located in laboratories, receive results, and compare them with simulations. This arrangement allows researchers and students to explore quantum algorithms without building their own hardware. It also provides feedback to hardware teams on the behavior of real devices under varied workloads. The experience resembles remote access to classical supercomputers in earlier decades, with the difference that the underlying physics is now quantum. While these systems remain limited, their presence in public and commercial settings marks a shift from purely experimental prototypes to early stages of deployment. These examples illustrate a broader trend. Quantum mechanics is no longer confined to a narrow domain of fundamental research. It has become a general framework for understanding and exploiting the behavior of many physical systems. Some technologies rely on simple consequences of quantization, such as discrete energy levels and selection rules. Others make use of coherence and entanglement in more direct ways. In all cases, the abstract theory supports and guides practical design. When a quantum device operates correctly, it provides not only a useful function, but also continuing confirmation that the underlying description of matter and radiation is reliable. At the same time, the fact that so much can be achieved while significant interpretative questions remain unresolved adds a layer of quiet tension. Engineers work successfully with quantities that have clear operational meaning, such as transition frequencies, coherence times, and error rates, while deeper questions about what quantum states represent in reality remain open. The presence of functioning quantum technologies, therefore, does not resolve the conceptual puzzles. Instead, it brings them closer to the surface of applied science. The same microwaves that flip qubits in a processor, or that probe resonances in an atomic clock, also act as probes of a theory whose basic objects are still being interpreted. The expanding suite of quantum tools thus serves both as a practical extension of human capabilities and as a continuing test bed for ideas about how the quantum world gives rise to familiar experience. In all of these discussions, a central question remains: how does the familiar world of stable objects and definite outcomes arise from a theory in which systems are described by superpositions and entangled states? In everyday experience, a chair stands in one place, a pointer on a dial indicates a single value, and a photon detector either clicks or stays silent. Quantum mechanics, on the other hand, allows states in which many possibilities coexist until a measurement is made. The standard rules say that when a measurement occurs, the state changes abruptly into one of the possible outcome states with probabilities given by the amplitudes. This sudden change, often called collapse, sits alongside the smooth deterministic evolution that applies when no measurement takes place. The coexistence of these two types of evolution within a single theory has long been a source of discomfort. It raises the question of what counts as a measurement and of how in practice the world manages to present definite results. A useful step toward answering this question comes from the study of decoherence. Decoherence does not introduce new postulates. It applies the usual quantum rules to larger systems that include not only the object of interest in the measuring device, but also their environment. In this extended view, there is no sharp boundary between system and apparatus. Instead, one considers how a quantum state spreads into many degrees of freedom through ordinary interactions. When a microscopic system such as a qubit or an atom interacts with a measuring device, the combined state becomes entangled. Different possible outcomes of the measurement become correlated with different macroscopic states of the device, just as in simple textbook treatments. However, in a realistic situation, the device is itself coupled to an environment made up of air molecules, photons, vibrations in the supporting structure, and internal microscopic degrees of freedom. Each of these interactions carries away a trace of information about which outcome branch the system has followed. Because the environment has so many degrees of freedom, and because these interactions are effectively irreversible on practical timescales, the different outcome branches lose the ability to interfere with each other. The off-diagonal terms in the mathematical object that describes the system and apparatus become extremely small when the environment is traced over. In more physical language, the phases that would be needed to produce interference between macroscopically distinct states are scrambled by the environment. The result is that for all practical purposes, the system behaves as if it were in a statistical mixture of distinct classical outcomes, rather than in a coherent superposition of them. Decoherence, therefore, explains why interference effects are rarely seen in everyday life and why macroscopic objects appear to have definite positions and properties. This process is not the same as explicit collapse. The global state of system plus environment remains a large entangled superposition that, in principle, evolves unitarily, according to the quantum equations. What decoherence shows is that observers who have access only to a small part of this global state and who cannot keep track of the detailed correlations with the environment will find that outcomes appear classical. Their effective description involves probabilities over apparently definite macroscopic states, with interference between those states suppressed to levels far below detectability. The familiar classical world thus emerges as an approximation valid when interactions with the environment are strong and when only limited observables are monitored. An important feature of decoherence theory is that it is not a simple smoothing out of quantum effects. It has structure. Certain sets of states, known as pointer states, prove to be robust under environmental interactions. These are states that, once established, tend to persist rather than becoming rapidly scrambled. For a dust grain, floating in air approximate pointer states correspond to reasonably localized positions. For a current in a measuring circuit, they correspond to definite ranges of current. The environment continuously monitors these preferred variables, and any superposition of widely separated values in these variables quickly decoheres. As a result, the macroscopic world is filled with objects that occupy stable pointer states. This explains why position and certain other classical variables play a special role in experience and in the design of instruments. The time scales involved in decoherence are often extremely short. For a macroscopic object interacting with a normal environment, the time required for a coherent superposition of different positions to decohere can be far shorter than any interval accessible to direct measurement. Even for mesoscopic systems such as small mechanical resonators or superconducting loops, decoherence times can be limited to microseconds or less unless exceptional isolation is achieved. This rapid decoherence is a key reason why quantum behavior is most easily observed in carefully shielded experiments and in systems that are cooled to very low temperatures. It is not that larger objects obey different laws, but that their many interactions with surrounding fields and particles erase quantum coherence so quickly that only classical-like behavior remains visible. Decoherence also plays a central role in practical quantum technologies. In quantum computers, quantum communication networks, and precision sensors, decoherence is the main source of error. Every unwanted interaction with the environment tends to leak information about the quantum state, turning coherent superpositions into mixtures. Engineering efforts aim to reduce these interactions as much as possible, to design hardware that naturally suppresses certain decoherence channels, and to implement error correction schemes that can repair the damage that does occur. The same theoretical tools that describe how classical behavior emerges from quantum laws are therefore used to estimate and mitigate noise in active devices. Understanding decoherence is not only a matter of interpretation, it is an engineering requirement. Despite these advances, decoherence does not fully resolve the measurement problem. It explains why certain superpositions become effectively unobservable and why macroscopic alternatives appear classical. It does not by itself explain why a single outcome is experienced in each run of an experiment rather than a continuing superposition of alternatives. In the global state of system plus environment, all branches remain present, each containing a version of the apparatus and, in principle, a version of any observers. Different interpretations of quantum mechanics offer different accounts of what this means. Some regard the branches as equally real components of a larger structure, while others treat only one branch as actual and the rest as possibilities that are somehow discarded during measurement. Decoherence provides the common background against which these views are developed, but it does not select between them. The emergence of classicality is therefore understood as a layered process. At the deepest level accessible to current theory, the dynamics of closed systems are governed by unitary evolution of quantum states. When a system interacts with its environment, entanglement spreads and decoherence rapidly suppresses interference between macroscopically distinct branches in the reduced description. For observers embedded in such a world, the effective behavior of macroscopic quantities is well approximated by classical equations, with probabilistic elements reflecting both quantum probabilities and practical ignorance. Measurement devices are macroscopic systems designed to couple specific microscopic degrees of freedom, such as the spin of an electron or the path of a photon, to robust pointer states that are then read as outcomes. In this way, the same quantum theory that describes single electrons passing through slits also describes the solid screen on which they are detected and the electronics that record their arrival times. The difference lies in scale and in the strength of environmental coupling. As scale increases and coupling strengthens, decoherence drives systems toward classical behavior. As experimentalists learn to isolate systems and to control their interactions, they reopen access to quantum regimes even for relatively large objects. Experiments with superconducting circuits, mechanical oscillators, and trapped ions have demonstrated quantum effects in systems with many degrees of freedom. These results reinforce the view that there is no fundamental boundary between quantum and classical, only a practical transition controlled by decoherence. This perspective reshapes the original questions that surrounded quantum mechanics. Early debates often focused on whether microscopic entities such as electrons obeyed different laws from macroscopic objects such as detectors and planets. The modern view is that the laws are the same, but that their consequences depend on context. When coherence can be maintained and environmental coupling is limited, quantum behavior dominates. When systems are large and noisy, classical approximations become accurate. The challenge shifts from asking where the rules change to asking how the same rules play out in different regimes. In doing so, it becomes clear that the emergence of the classical world is not an additional postulate, but a result of quantum dynamics in complex systems. Even with this understanding, some fundamental issues remain. The theory provides no unique definition of what counts as the environment or of exactly when a measurement has occurred. Choices about how to partition the world into system, apparatus, and environment are made according to practical convenience. In most situations, these choices lead to the same predictions, but conceptually, they leave open questions about the status of the global quantum state. Furthermore, while decoherence explains why interference between different outcome branches is suppressed, it does not specify why an observer should find one particular branch realized rather than another. These questions lead directly into the domain of interpretation, where different schools of thought propose different ways of connecting the formalism to experience. Before turning to those broader views, it is useful to summarize the situation reached so far. Quantum theory offers a unified description of microscopic and macroscopic systems. Decoherence explains how, under typical conditions, this description gives rise to the appearance of classical behavior. What remains unresolved is how to understand the connection between the global quantum state that the theory assigns to the world and the definite experiences that observers report. The tension between these levels of description continues to motivate new ideas, experiments, and proposals for deeper theories that might one day integrate quantum mechanics with gravity and with a more complete account of space and time. The picture assembled so far is internally consistent and strongly supported by experiment, yet it remains incomplete as a description of reality. Quantum mechanics provides rules for assigning states, for evolving those states in time, and for extracting probabilities for measurement outcomes. These rules have been tested in many regimes and have passed each test with high precision. Decoherence explains how classical behavior can emerge for macroscopic systems. Entanglement and superposition, once considered puzzling oddities, now serve as working resources in quantum technologies. Still, the theory leaves open what its mathematical objects represent and how exactly they relate to the world that is experienced. This gap is not a small detail. It motivates distinct lines of interpretation that try to answer in different ways what a quantum state is and what it means for a measurement to occur. One traditional approach treats the quantum state as a tool for calculating probabilities, with limited commitment to any deeper picture. In this view, the state summarizes information about preparation procedures and about expected outcomes of possible measurements. The collapse rule is regarded as an update of this information when new data are obtained. The focus is on the link between experiments and predictions, rather than on a detailed account of underlying processes. This stance often goes together with careful attention to the domain of applicability of concepts such as position and momentum, emphasizing that these are defined operationally by the arrangements used to measure them. The success of the theory in guiding and explaining laboratory work is taken as its central justification. Questions that go beyond this laboratory context are treated with caution. Other approaches attempt to give a more direct ontological role to the quantum state. One example is the class of interpretations in which the state of the entire universe evolves unitarily at all times without collapse. In such views, the branching structure produced by decoherence is taken seriously. Each branch corresponds to a different pattern of outcomes for measurements, and all branches are considered part of the total description. Observers are then associated with structures inside this global state. Their experiences correspond to particular branches in which they find definite results. From this perspective, probabilities are related to the relative weights of branches. The challenge becomes to explain why observers should assign these weights in the same way that the standard rules prescribe, and how the familiar notion of a single shared world arises from this branching structure. There are also interpretations that modify the dynamics of quantum mechanics. In objective collapse models, for example, the equation governing state evolution is supplemented with additional terms that cause superpositions of macroscopically distinct states to collapse spontaneously, even in the absence of a measurement apparatus. The collapse events are random, but occur with frequencies and strengths chosen so that microscopic systems behave almost exactly as in standard quantum mechanics, while large superpositions are suppressed. Such models aim to remove the need for a separate measurement postulate by building state reduction into the dynamics. They make slightly different predictions from the standard theory, especially for carefully constructed systems that maintain superposition over large scales or long times, and experiments search for these deviations. Another line of thought keeps the usual mathematical structure but supplements it with additional variables that specify definite properties at all times. In these hidden variable or pilot wave theories, the quantum state plays a dual role. It guides the evolution of the extra variables, such as particle positions, while also determining the statistical distribution of outcomes. The hidden variables are not directly accessible in all situations, but their presence restores a kind of realism in which particles follow definite trajectories. To match observed violations of Bell-type inequalities, these trajectories must be influenced by non-local effects. The behavior of one part of an entangled system can depend on the configuration of another part at a distance. This non-locality does not allow controllable, faster-than-light communication, but it does represent a departure from simple local pictures. Alongside these more established interpretations, there are approaches that attempt to reconstruct quantum theory from informational or operational principles. Instead of taking the mathematical formalism as given, they start from high-level constraints on how information can be acquired, processed, and combined. For example, they may impose that certain tasks, such as perfect cloning of states or instantaneous signaling, are impossible, while others, such as secure key distribution, are allowed. From these constraints, they derive the structure of state spaces, measurements, and dynamics. In this picture, the quantum state is viewed as encoding probabilities for outcomes of idealized measurements under specified conditions, and the unusual features of quantum theory are traced back to basic rules about information. This program does not yet answer all foundational questions, but it provides an alternative route to understanding why the theory has the form that it does. These differing views share the same core mathematical machinery and make the same predictions for all experiments performed so far. They diverge in their stories about what exists and about how the formalism connects to reality. For some physicists, this plurality is acceptable as long as the theory maintains its predictive power and supports technological development. For others, the lack of a single clear picture is unsatisfactory, especially when quantum mechanics is considered as part of a deeper quest to understand the universe as a whole. This tension becomes sharper when quantum theory is placed next to general relativity, the current theory of gravity. General relativity describes space-time as a dynamical entity curved by energy and matter. Quantum mechanics, in its standard form, describes fields and particles evolving against a fixed background. Bringing these two frameworks together consistently remains an open problem. Efforts to construct a quantum theory of gravity explore several directions. Some approaches quantize the gravitational field in analogy with other fields, leading to theories in which gravitons, the quantum excitations of the gravitational field, play a role. Other approaches, such as loop-based models, start by quantizing geometric quantities, directly suggesting that areas and volumes may have discrete spectra at very small scales. String-based theories replace point particles with extended objects whose vibrational modes correspond to different particles, including the graviton, within a higher dimensional spacetime. In all of these cases, the usual quantum rules are applied to new degrees of freedom, and the question arises of how measurement, decoherence, and entanglement operate when spacetime itself is subject to quantum uncertainty. Black holes provide a particularly sharp intersection between quantum theory and gravity. According to classical general relativity, a black hole is a region from which nothing can escape, bounded by an event horizon. Quantum field theory in curved space-time predicts that black holes emit radiation with a thermal spectrum now known as Hawking radiation. Over very long times, this radiation can cause a black hole to lose mass and eventually evaporate. The apparent loss of information about the matter that fell into the black hole during this process raises what is known as the black hole information problem. If the radiation is purely thermal and uncorrelated with the initial state, then information seems to be destroyed, conflicting with the usual requirement in quantum mechanics that evolution be unitary. Various proposals attempt to resolve this tension by suggesting that subtle correlations are present in the radiation, that information is stored in new degrees of freedom associated with the horizon, or that the semi-classical description breaks down in important ways. None of these ideas has been definitively confirmed. Another area where quantum theory and space-time intersect is the study of entanglement in quantum field theories and its relation to geometry. Calculations show that the entanglement between degrees of freedom in different regions of space follows patterns that are sensitive to the geometry and connectivity of those regions. In some theoretical constructions, the entanglement structure of a quantum state appears to be closely linked to the emergent properties of a space-time in higher dimensions. These ideas are still being developed, but they suggest that space and time themselves might arise in some sense from more fundamental quantum relations. If so, quantum mechanics would not simply be a theory defined on space-time, but also a theory from which aspects of space-time could be derived. At the same time, quantum theory is being tested in regimes that were once considered purely classical. Experiments with ever larger systems in superposition with more massive objects in interferometers, and with entanglement maintained over longer distances and times, aim to push the boundaries of the theory. Some proposals suggest that gravity might cause an intrinsic collapse of quantum superpositions for sufficiently massive systems, leading to observable deviations from standard predictions. Others look for tiny violations of known symmetry principles, or for modifications of quantum dynamics at very high energies. So far, quantum mechanics has continued to match experimental results, but the range of tests is expanding. Each new regime explored either confirms the existing framework or points to new physics. In parallel with these fundamental investigations, quantum mechanics continues to guide developments in materials communication and computation. Quantum technologies, even when they do not yet surpass classical devices in performance, act as demonstrations that controlled manipulation of quantum states is possible beyond the simplest systems. Each improvement in coherence times gate fidelities and network connectivity extends the domain in which quantum rules are not only relevant, but dominant. The boundary between fundamental experiments and applications blurs as devices built for practical goals also serve as platforms for probing the theory. The situation taken as a whole is one in which the mathematical structure of quantum mechanics is well established and deeply integrated into many parts of physics and engineering, while its interpretation and its ultimate place in a more complete theory of nature remain unsettled. The theory describes a world where probabilities are intrinsic, where superposition and entanglement link possibilities in precise ways, and where classical behavior emerges through decoherence in complex systems. It also leaves open whether the quantum state is a complete description of reality, how many branches of history might be associated with a given state, and how space-time and gravity fit into the same framework. From the level of individual electrons passing through slits, through entangled pairs separated by large distances, to assemblies of many qubits in prototype quantum processors, the same formalism applies. It has not yet failed any careful test. At the same time, it points beyond itself, hinting at deeper structures that are not yet fully understood. The interplay between precise prediction and open conceptual questions gives quantum mechanics a distinctive position in modern science. It is both a mature working theory and an active area of foundational research. The devices that depend on it, from atomic clocks to quantum sensors and early quantum computers, are practical confirmations of its power. The unanswered questions about what it ultimately means and how it connects to gravity and to space-time keep the field open, inviting further exploration. In this sense, quantum physics remains, even after many decades, not a finished story, but an ongoing investigation into how nature behaves at every scale that can be reached. The world that quantum theory describes is quiet and precise. Particles and fields follow rules that are written in compact equations, yet those rules allow behaviors that seem far from everyday intuition. Superposition, entanglement, interference, and decoherence all emerge from the same underlying structure. In small, well-isolated systems, their effects are sharp and visible. In large, noisy systems, they blend together to produce the familiar classical picture of stable objects and predictable motions. The same principles that govern an electron in a double-slit experiment also govern the atoms in a clock, the circuits in a computer, and the signals in a communication link. Seen in this way, quantum mechanics is not a separate layer added onto an otherwise classical world. It is the common framework from which both microscopic and macroscopic behavior arise. Over the past century, many of the surprises that first accompanied quantum theory have become standard tools. Entangled photons test the limits of locality. Superconducting loops host qubits in processors. Ultra-cold atoms simulate materials that are difficult to calculate in detail. Atomic transitions keep time for navigation systems. Each of these applications depends on careful control of systems that, according to the theory, never fully lose their quantum character. In parallel questions about what the quantum state represents, how measurements select outcomes, and how gravity fits into this picture remain open. Competing interpretations and speculative extensions share the same experimental base but offer different images of reality behind the calculations. None has yet displaced the core formalism that matches data so well. The current situation is therefore mixed in an interesting way. On one side, quantum mechanics is a settled part of working physics and engineering used every day to design devices, interpret experiments, and explore new regimes. On the other side, it is an unfinished account of nature, with edges that touch deep questions about information space-time and what it means for something to be real. Between these two aspects lies a wide field of ongoing work, where new experiments probe larger systems, new devices extend control over fragile states, and new ideas attempt to connect the formalism to a more complete picture. For now, quantum physics stands as a reliable guide and an unresolved mystery. At the same time, a theory that explains much of what is observed while still pointing toward phenomena and principles that have not yet been fully uncovered.